Okay, let's get started. Welcome, everyone. In this session, I will share with you our best practice on scientific on OpenStack. Today's topic, I will talk about a collaboration between Intel, Shanghai Jiao Tong University, and 99 Cloud on OpenStack at the predictive data mining and climate medicine with dynamic HPC on Shanghai Jiao Tong University HPC Cloud. This is today's agenda. First of all, I will give you an introduction about our three parties, Intel, 99 Cloud, and Shanghai Jiao Tong University. Second, I will talk about the background of this project, why we are going to build a dynamic HPC cloud, what kind of problems it's going to resolve after we are finished this POC. And then Leon will help to go through the detailed technical on how to integrate OpenStack and OpenHPC. And he will also cover the future work after this project. And at last, I will show you the demo of our POC, and we will definitely have a Q&A sections at the end. So my name is Shu Quanhuan. I'm a technical director from 99 Cloud. I focus on helping the enterprise landing their OpenStack solutions and migrate the data and application to the cloud. Also, I'm a join OpenStack community since 2011 as a ATC speaker and track chair. And Dr. Luo from the Jiao Tong University, he cannot attend this summit this time. He is focused on, he received his BS, MS, and PhD degree from the Shanghai Jiao Tong University. His focus area is cloud computing, HPC, SDN, and data analysis. And Leon from Intel.
Yeah, my name is Leon. So I'm a senior software cloud architect. I work for Intel, the Open Source Technology Center. So I've been doing in the cloud computing area for quite some time. So my PhD is about multi-cloud orchestrations. So later on, we'll just share some of the information, the work that we have done with Intel, 99 Cloud, and Shanghai University about how do we enable the OpenHPC on OpenStack Cloud.
Okay. So the background. First of all, we have close working with Shanghai Jiao Tong University. In university, there are many college or institutes. They have their own small data centers. Those data centers has their own administrator to manage those resources for providing the compute, storage, networking for the researchers or professors to do the scientific work. But the hardware is distributed with low utilization around the whole university. And different colleges, such as the computer science and the biology, they cannot have great conversation or even share data between them. So there is the problem the Shanghai Jiao Tong University network center they are going to resolve. They want to aggregate all the resources together and then can provide a centralized platform to different college or institute. And then the researcher can just apply the resources from the centralized portals so that the teachers can focus on their scientific research and do not need to worry about the operation work. By this way, we can make sure the SLA is guaranteed. The researcher or professor do not need to worry about the services is done in the midnight. And also, we can make sure the energy consumption is low and have a very low high failure rate during the whole operation. And as I just said, the mission of the cloud services is to centralize all the hardware, improve the overall user experience by no matter you are doing the HPC kind of work or any education services or hosting any education applications, and provide these stable IT hosting services within the whole university. Furthermore, the Jiao Tong University, they also plan to provide the services outside the university to some medicine institutes in Shanghai or even in China. So as we see in the picture in the right, different colleges, they share the different resources in those on the hardware, and you can see the percentage is very high in the blue. That is the computer science computer science, and for the scientific research, that is the lowest, right? Because those professors do not have the professional operation experience, so even they have very huge requirement on how to use the computing resources, but they cannot operate a very big cluster to fulfill their HPC requirement. So we are going to establish a cluster for the whole campus. Shanghai Jiao Tong University has established a HPC cluster about 400 nodes since 2015 to provide the services within the university. But the HPC cluster currently, the status that is dedicated. For example, the scientific research, they have very huge requirement. So they will ask the networking center to provide those cluster to them to use. But if there is another institute going to ask another cluster, the networking center, they do not have the agility or have the capacity to provide another HPC cluster very soon to meet the requirement. And also to set up a HPC cluster is very complicated, including, as you see, the different drivers, different HPC software stack. So the problem is that how can we provide a HPC cluster in hours or in minutes to fulfill the requirement of different research institutes, such as the climate medicine or some biology, the genomics analysis, etc. So the problem we are going to resolve we have to look at different software or open source software to see what kind of software stack can help to resolve it. And another problem is that how can we provide the different isolated environment to the cluster so that the different institute can use the isolated environment and do their research just in an isolated environment. That is very important. So to summarize it, that is the multi-tenancy problem in the HPC environment. So we can summarize several requirements on the HPC in Shanghai Jiao Tong University. First one is, as I just mentioned, multi-tenancy and self-services. And the second is how to more flexible to manage the HPC cluster, including provision, scaling, and scaling. And then how can we improve the overall improvement? Because some small institute, they just run small HPC work in that cluster. We can use the time. How can we sharing the same cluster for different small institutes? And the fourth is how to manage the HPC workload. because different HPC workload, they will require different binary, or they will require the optimized binary. So we have to provide the environment for different HPC workload. And the last but not least is how can we make sure the throughput of the environment. So we are talking with Intel. Intel has contributed on the OpenHPC, and Leon will help to share with us how OpenHPC can resolve this problem for us.
Yeah, thank you, Suchen. So over the next few slides, I'm going to explain how we use some of the open source technologies that we can apply into the HPC environment. So one of the open source project I want to mention here is OpenHPC. I'm not sure any one of you are familiar with OpenHPC. Anyone know OpenHPC? Yeah, cool. Okay, so OpenHPC basically is a Linux Foundation project, as you can see here. So the missions of this OpenHPC project basically would like to provide a reference collections of HPC software, open source software, and make it easier for people to learn and to use, to deploy HPC in their environment. So as you can see from the vision over here, I just want to highlight that basically OpenHPC itself is not a new software. OpenHPC basically provides a collections, basically like a package repository for different open source HPC components that can be used together. So they provide a recipe and some guidance and some best practices on how to use or deploy HPC how to deploy HPC software to meet the HPC requirements. So for more information about OpenHPC, this is the link that you can go there. I'm not the one that contributing to the OpenHPC itself. So we have a separate team. At Intel, we have a different team that focusing on OpenHPC contributions. So we have a project lead and maintainer that contributed to the OpenHPC repositories, OpenHPC repository itself. So these are all the companies that are contributing to OpenHPC. As you can see, it's not just Intel. So ARM is also supported. And maybe one thing that I can add here is I think Red Hat recently also joined this OpenHPC project. So it's a community effort. So we support a wide range of hardware and software and vendors to support this project. So as I say just now, OpenHPC itself is not a software, but it's a combination of different tools together and build out a common recipe so that people can use easily deploy OpenHPC in their environment. So if these are some of the commonly used software in the HPC environment. So if there's any additional software, open source software that you would like to be part of the OpenHPC, there is a submission link there on GitHub. You can actually request to include that particular open source software into the OpenHPC software stack. So as I mentioned just now, so basically OpenHPC provides there's a list of OpenHPC recipe they can use. For example, let's say someone are interested to use Werewolf and PBS professionals. There's on CentOS. So there is an install guide and recipe to tell you how to provision that environment with Werewolf, PBS on CentOS. Or if any other people want to utilize like Werewolf and Slum, there's also another recipe on that. And if you're working on SLES, then there's another different kind of recipe that you can utilize on that. So what we have done here is we actually provide a recipe here that actually integrate OpenHPC on OpenStack running on CentOS. So how do we make OpenStack and OpenHPC to work together? So in general, in summary, we're actually using OpenStack-ironic. OpenStack-ironic is the bare metal service provisioning. So there are two models that we tested here. Is one thing is you have a existing OpenStack cloud environment, and you're using Ironic to do bare metal provisioning, and then you're basically using the bare metal provisioning tooling to spin up the HPC head node and the compute node in the cloud environment. So everything is actually deployed in the cloud, bare metal cloud environment. So this is the first scenario. So the controller here is basically the OpenStack controller. It's not a HPC controller. So this is the OpenStack platforms, OpenStack controller that actually spin off additional compute nodes using Ionic so that everything can still be deployed on the bare metal machines. The second scenario is more about Cloud Burst scenario. So assuming that you have an existing HPC environment in your on-premises environment, so you have your head node and compute node already in your cluster, but sometimes there's a higher demand or high load coming in that existing environment cannot satisfy, then you actually can burst the compute node into the OpenStack cloud environment, which is being provisioned. I mean, all this compute node is being provisioned by the OpenStack bare metal cloud. So you're basically bursting the compute capacity into the cloud. So these are the two scenarios that we have done the POC for that. So in general, so these are the integration process basically consists of 3 phases. So the first phase is about image building. So we use this image builder to build up the HPC images that is required for the head nodes and the compute nodes. So that's the first phase, about image building. And the second phase is about using the OpenStack Ionic Cloud to provision the bare metal machines that is required for the HPC environment. And the third phase is basically installing all the OpenHPC packages and libraries on those bare metal machines that has been provisioned. So generally, there's 3 phases. As you can see here, so we're using always using the same consistent environment here. That if you go back to the previous 2 scenario, so this is running HPC on the cloud. This is bursting existing HPC to a cloud. And the recipe that we provide here is always consistent no matter which one you use, okay? So you can see the step 1 here is about step 1 for the Cloud Burst scenario, and the step 1 also is for the HPC service in the cloud. Basically, it's about preparing the images, the phase 1 that I mentioned just now. And the second phase is about deploying the image with Ionic, the second phase here. Second phase for the Cloud Burst scenario and the Cloud Burst and the HPC as a service scenario. So basically, it's about provisioning the bare metal nodes that was coming from the images that we have built in the previous phase. And then the last phase is basically about configuring the HPC, OpenHPC environment. So it will give user a consistent interface, no matter you want to do a Cloud Burst scenario or the cloud-based scenario. So we have open sourced this Cloud Toolkit on GitHub. So we would like to invite any interested party to give us a feedback and provide us, or even if you want to contribute to this Cloud Toolkit, we are mostly welcome, and we can collaborate with 99 Cloud as a community effort. So going back to the previous architecture just now, so all this Cloud Toolkit right now, the 0.7 versions that we released here is basically using, for the phase 2, remember the 3 different phases that I talked about just now? So the phase 2 process, in the 0.7 version, we're actually using the pack stack, the Red Hat RDO pack stack. But moving forwards, we are actually using Cola. We're moving into a Cola container-based deployment to spin off the Ionic Cloud environment. So that gave us a more flexible way to support various OS and containerizing the OpenStack deployment structures. That's why we work together very closely with 99 Cloud. They are one of the vendors in China to support Cola, right?
Yeah.
So moving forwards, we are focusing on using Cola to deploy the OpenStack Cloud environment, and then writing some playbooks and to deploy the OpenHPC libraries. So there's a mailing list over there, so we welcome anyone to subscribe to the mail list and work with us together. So I want to spend some time to show you a demo. It proved that it works. So I actually presented this last time in Boston, but last time there's only a 10-minute lightning talk, so I didn't get a chance to show all the demo. So as you can see here,
the steps shows here is the phases you just mentioned, right?
Yeah, so this is the very first phase. They're trying to prepare the images.
We will skip the image, disk image builder part because it takes time.
Yeah. Is this image builder? Is this just test suite? No, that's the end.
Yes, he remembered the last time.
Yeah, that's the end. That's the final step.
Okay.
Testing the suite. Yeah, so this is the first step. That is build the HPC images.
Yeah.
So the second phase is about provisioning the head node and compute nodes. And the third phase basically is running the whole HPC. So the first step here, trying to build install HPC RPM images in the images. So we pre-package all the HPC library in the images so that later on can be deployed by the bare metal nodes. So that's you can see here there's an SMS node here. That is the head nodes images for the head nodes. So the second phase is about Cola. This is the one that we move over to Cola. We're using Cola to build up the bare metal cloud environment. So if you are familiar with the OpenStack Ionic, there's an Ionic node list and using Nova boot to spin out the Nova instances on bare metal.
This is a script to put all the nodes, use the Ionic to enroll those nodes.
Yep. And that including setting up all the HPC network that you have, the network that you have seen in the previous diagram. So they're still deploying. Yep, that is. Yep. So this is still trying to enroll the bare metal nodes into the environment. So it's still creating some of the port requirement. The glance images. So we actually registered the phase one, the disk image builder. We registered those images into the Ionic, into the glance, OpenStack glance. So right now, over there, we actually enroll one head nodes and two compute nodes. So this is part of the enrolling process. So all this is the second compute nodes.
Yeah. This demo is show use the command line. Of course, you can use the GUI, use any OpenStack distribution.
And fast forward a bit.
Fast forward, right?
To the next phase. Then stop. Oh, there's a problem with the video just now. Okay. So now we come into the provisioning the. After you enroll the bare metal nodes, you need to provision those nodes. So enrollment and provisions are two different phases in the Ionic process.
Yeah.
So right now is waiting for Nova and the head node to be ready. So in this POC, we're actually using the head node with the NFS as well. So see there's 3 nodes over here, which has been enrolled. Yeah, there's 3 nodes here.
So it's installing the image to the bare metal.
Yeah. So that's the first one. See the power on. It's waiting for the head node to be ready. It's active. So you can see the nova list. You can see that head node is already active.
Yeah.
Sorry, I went too fast. Yeah. See that? So now it's booting out the compute nodes, which is CC1 and CC2. So once that compute node is booted out, it'll actually boot out with compute node images that we have built in the phase one. And that will register, I think this one is using Slum, to register Slum into the Slum clusters. So 2 nodes are powering up right now. It's power on, waiting. Yeah, it's active right now. So everything is up. Okay. So right now, the last step, what we want to show here is just to do a simple OpenHPC testing. OpenHPC software itself there's a test suite in the OpenHPC, so you can run the test suite to validate all the libraries, all the recipe that you want to use in this environment.
Yeah, as you just see, we download the test suite, right, and run one MPI testing.
Yeah, so there's a lot of tests that you can run. If you run a full test, it can probably take like 2-3 hours. But in this example, they actually disabled a lot of tests and only run one test. So what we're showing here is try to set up a testing suite environment from the controller nodes. So there's a test folders over there that you can run. So basically, it's running FFTW testing. So that's installing the test suite right now. So we got the test suite report. Executing the test. Over here.
After launch the test show, you can see there are testing process in the in those 2 computer nodes.
So this is the test that I copy for over from controller nodes. Yep. So this is the actual test we tried to run. Yep, this one. Over here. And then finally we'll run this. Yep, that's the one. This is basically just proof that the OpenHPC software library is all installed and you're able to run FFTW. Okay. And you can see that some process will be running over there.
Yeah.
Any questions? Come. 我听不到。
你这个应用呢有什么？应用一个 OpenHPC 啊，它这个应用啊有什么？是针对特定的应用吗？还是针对什么类型的应用？有什么特定的场景吗？
So the question is like, is this application being used in specific areas or specific scenario? So that's the thing that Suchun has explained previously. So because the different HPC users have a different requirements. Some might run at different HPC libraries. So by using OpenHPC, you can select individual library that the users are interested on and then run on this environment. So it depends on the user needs. So 就根据不同用户的需求，他们就可以选择他们所需要跑的那个 HPC 的library， 因为每个用户都会使用不同的 library。对，是的 ，It's a common architecture, it's common platforms for all the users to use with a same interface. So I'm trying to translate in both languages. Yeah. Any other questions? So in this POC, we use NFS, but yeah, so that's the next thing that we're working on Lustre. So we'll try to put out the Lustre integration in the recipe as well. So we know that Lustre is a common use case in HPC. And also we try to integrate OPA driver natively in the recipe as well. Because right now in the POC, basically just using Ethernet. Yeah.
Yeah.
So OPA and Lustre are the ongoing work that we are working on right now.
Any other questions? No. Okay. Thank you today.
Thanks very much. Thank you.